Okay. Today's video is going to be short because I have a couple of reasons. First, this is the last video before the exam. I don't want to overburden you with a lot of new material. There's no point covering material which is not going to be on the exam because that'll just stress people out. You might forget it by the time we cover it, by the time we get back to it. And also because I think the material that is about to be covered is quite interesting, and it would be better to cover it in its own starting Tuesday rather than cover some of it now and some of it later. Right, so the last thing we were looking at was cyclic groups. Cyclic groups. Okay. So let G be a finite group of order Q. Finite group of order. Well, fine, I'll say Q. Written multiplicatively. Wait. So far we have been using M, so I'm just going to go back to M. Written multiplicatively. Okay. Let G be some element of G. Then consider the set, the subgroup generated by G, which is the set G to the 0, G to the 1, and so on. Okay. We know G to the M is equal to 1 is equal to G to the 0. So the set has less than or equal to M elements. Okay. If the set has exactly M elements, then it's all of Q. Then all of G is all of G. In this case, we call this case, say, G is a generator of G. And if G has a generator, if G has only exactly one generator, has exactly one generator, we say G is okay, that is false. G has a generator, we say G is cyclic. We say G is cyclic. Okay. And we saw some examples. For example, in Z5 star, we had which was 1, 2, 3, and 4. Identity was 1, 2, and 3 were generators. Okay. And 4 was not a generator. 4 is not generator. The group generated by 2 was 2, 4, 3, 1. And when generated by 3, it was 3, 4, 2, 1. Whereas the subgroup generated by 4 was just 4 and 1. Okay. Now, let me define something. Define H belonging to G is called a subgroup of H, subgroup of H, if H contains, if H satisfies all the group axioms, while for the same operation as G. Okay, so for example, the integers is a subgroup of R. Okay, because what are the four conditions? Integers are closed, closure, existence of identity, inverses, and associativity. Right? That's one. R greater than 0 under multiplication is not a subgroup of R, subgroup of R, even though R greater than 0 is a group on its own. Group. That is because the operation is different. Because the operation is different. Okay? In general, the subgroup generated by G is a subgroup of G. Okay? And is equal to G only if G is cyclic with small g as a generator. For example, if I look at the group Z6, which is 0, 1, 2, 3, 4, 5, 1 is a generator, 1 is a generator, right? And it generates the group 1, 2, 3, 4, 5, 0. However, 2 is not a generator. The subgroup of generated by 2 is 2, 4, 0. So the subgroup generated by 2 is a proper subgroup of Z6. Okay? Note the n, maybe not note. The n is always cyclic. Is always cyclic. For any n. For any n. One is always a generator. Okay. Theorem. Any group of prime order is cyclic and every non-identity element is a generator. Okay. I am not going to prove these theorems because they are because we are not doing a group theory course. They are really good results. The book might have a proof for this. I don't know. I want to show you something slightly more interesting, which is why I'm skipping over the proof. But this is a very important result. If P is a prime, if P is prime, then ZP star is cyclic. Okay. Now note, cardinality of ZP star, the order is P minus 1, which is not prime, for P greater than 3. So it does not immediately follow from the previous theorem. These are two separate theorems, okay? But this is showing that every group is cyclic, okay? Every group of prime order is cyclic, okay? This also leads to a corollary. Every group of prime order is abelian. Okay? Proof. Every cyclic group is abelian. Every cyclic group is abelian as g to the a times g to the b is equal to g to the a plus b, g to the b plus a is equal to g to b times g to the a. Right? So if I want to look at an example of a non-abelian group, I have to look at a group of non-prime order, right? So example, so let me give you an example of a group that is not cyclic. Example of an abelian group that is not cyclic. Okay. All the examples Zn are all cyclic, right? That is, my previous theorem says that every Zn is cyclic. So I can't find an example there. But let us look at R2, which is the set of all numbers x, y, such that x belongs to R, y belongs to R. Okay, the real plane. Then this is an abelian group which is not cyclic, Okay, it is easy to see that it is an abelian group. Identity is 0, 0. Closure is obvious. X, y plus x1, y1 plus x2, y2 is equal to x1 plus x2, y1 plus y2 belongs to R2. Inverse x, y to the negative 1 is equal to minus x, minus y. And associativity is also there. Right? However, no single element generates it. No single element generates R2. Right? Any single element is always going to generate just one line. Every multiple of x, y is going to look like lambda x, lambda y, and so it's not generated by a single element. In fact, it's quite easy to say that even R is not generated by a single element, or even rationals are not generated by a single element, but you can say this. So let me do this. Let me do not R2, maybe Z2. Z2. XY axis. X, y axis belongs to Z2 and generates Z2, which is nx, ny. Right? The group is generated by by 1, 0 and 0, 1 together. Okay? This group needs at least 2 generators to form. So when I say AB, this is equal to NA plus MB. Okay? N, M belong to Z. So I'm writing additively, or A to the N, B to the M if I was writing multiplicatively. So it's everything of this form. Such a group is called group is called finitely generated. Every group is finitely generated. You can just list out all the elements and call them generators. So this is only true for infinite groups, so you don't really need to know this detail. Remember this detail. I'm just stating it in any way. Okay. But with that, I can now show you example of a non-abelian group. The finite group. Okay. I've already said that a group which is generated by just one element is going to be always abelian, right? It's going to be cyclic, and cyclic groups are all abelian. So look at the group generated by G is equal to 1a b and the following properties: a times b, well, a squared, a times b, a squared times b. Okay, with a squared is equal, a cubed is equal to 1, a cube is equal to 1, b squared is equal to 1, and a squared b is equal to b times a. Okay, claim this is a group. This is a group under dot. Clearly this is not abelian because a squared b, if it was abelian, should be equal to b times a squared rather than b times a, and a squared are different elements, right? So let us try to show that it is closed. Closure. Closure. Okay, I'm not going to show it for every single element. I'm just going to show that, well, 1 times anything is the same. I am going to show how to do it. I'm going to show how you multiply by a and b, okay, from the left. For everything else, you can extrapolate from it. A times a is equal to a squared. A times b is equal to ab. A times a squared is equal to a cube, which is equal to 1. A times ab is equal to a squared b. Well, let me just write it here. Maybe. A times ab is equal to a squared b. A times a squared b is equal to a cube b, which is equal to 1 times b is equal to b. And a times 1 is equal to 1. Great. What about b? B times a, so let me start with 1. Actually, b times 1 is equal to b times 1, so that's b. B times a is by definition equal to a squared b. B times b is b squared, which by definition is equal to 1. Then b times ab, a times b, is equal to ba times b, which is equal to a squared times b is equal to a squared times b squared is equal to a squared. Which is equal to a squared times 1 is equal to a squared. B times a squared b is equal to b times a times b. Well, b times a is a squared b times a times b is equal to a squared times b times a times b, which is equal to, well, b times a is a squared b, so a squared times a squared b times b, which is equal to a to the 4 b squared, which is equal to, well, a to the 4 is a times a cube times 1 is equal to a times 1, which is equal to a. Okay? And what's the final one left? Did I do b times b? Yeah. B times 1, b times a, b times b, b times a, b times a squared b, b times a squared. I forgot to do b times a squared. Well, b times a squared is equal to b times a, which is a squared b times a, which is equal to a squared times b times a, which again is a squared times b, which is a times a cubed b, which is equal to a times 1 times b, which is ab. Okay, so it is closed. Identity is 1. Identity is 1. Inverse. I'm going to let you check every element has an inverse. Check every element has an inverse. So even though this problem is not on homework, so there is no homework this week. Homework. Check this as a group. Check this is a group. Okay. You have to assume that dot is associative and dot is associative. So you're given that dot is associative, otherwise things you can't make use of things. So you have to assume that dot is associative, but otherwise you have to check all these three conditions, and I'm leaving you to check that indeed other two conditions, that is to say closure works out for every single element, and that every element has an inverse. Okay, then we come back to finite groups, which are abelian and generally cyclic. Uniform sampling. Given G, which is a cyclic group, CY cyclic group G of order M, along with generator G, it is easy to sample a uniform H belonging to G. Easy to sample uniform H belonging to G. How do you do that? Well, choose a uniform x belonging to 0 to m minus 1 and set h is equal to g to the x, well, defined as g to the x. Right, this is going to go through the entire set. So since you can choose a uniform element from the group, we can now define the discrete logarithm problem. So fix a group again with generator G, blah, blah, blah. So discrete logarithm problem. Discrete problem. Fix cyclic group G of order M and generator G. We know that the subgroup generated by G, which is G to the 0, G to the 1, dot, 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 G to the M minus 1, is equal to G by definition, which is to say for every H belonging to G, there exists a unique X belonging to Z M such that G to the power X is equal to H. In that case, define log to the base G of H to be X, the discrete logarithm GARI, logarithm of H with respect to G in the group G. Okay? So for example, in Z11 star, by theorem, this is cyclic. What is log 2 of 9? What is log to the base 2 of 9? Well, let us look at what the subgroup generated by 2 is. We know it's going to be, well, 2 to the 0 is 1. Okay. 2 to the 1 is 2. 2 to the 4 is 2 to the 3. 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16, which in 11 is 5. 2 to the 6 is 32, which is 10. That was 2 to the 5. Yes. 2 to the 6 is 64, which is, well, 10 to the 20, and that is 9. So I can in fact just do twice. 4 to the 8, 8 to the 16, which is 5, 5 to the 10, 10 to the 20, which is 9, 9 to the 18, which is 7, 7 to the 14, which is 3, 3 to the 6, which is 6, 6 to the 12, which is 1. And so, therefore, log to the base 2 of 9 is 1, 0, 1, 2, 3, 4, 5, 6. Now, what is log to the base 8 of 9? Let us compute the group generated by 8 in order. 1, 8. 8 times 8 is 64, which is 9. 9 8s are 72, which is 6. 6 8s are 48, which is 4. 4 8s are 32, which is 10. 10 8s are 80, which is 3. 3 8s are 24, which is 2. 8 2s are 16, which is 5. 5 8s are 40, which is 7. 7 8s are 56, which is 1. So that is my group. So log to the base 8 of 9 is 0, 1, 2. Okay. Another example. In Z13 star, what is log to the base 2 of 9? Let's see how it changes when I change the group. Well, what is the group generated by 2 now? 1, twice of that is 2, twice of that is 4, twice of that is 8, twice of that is 16, which is 3, twice of that is 6, 2s are 12, 2s are 24, which is 11, 2s are 22, which is 9, 2s are 18, which is 5, 2s are 10, 2s are 20, which is 7, 2s are 14, which is 1. And so, log to the base 2 of 9 in Z13 is actually 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay? So it depends on the group. So what is the discrete logarithm problem? Informally, formal, discrete logarithm, D-log problem in G. Given generator G, and an element H, and element H, compute log to the G of H. And D-log assumption, Solving the discrete log problem in G is hard. Solving the discrete log problem in G is hard. Okay? So I will not formally define the discrete log problem because The Diffie-Hellman problem is based on the discrete log problem. You'll probably need a refresher for that anyway on Tuesday after the exam. So I'm not going to I'm not going to go into that right now. Regarding the exam, this is the material that we are going to cover till it. So groups are a part of the exam, and groups are a simpler part of the exam. So expect questions on groups. They're fun. They're easy to compute. They're not going to be super proof heavy questions, right? Not abstract questions, much more concrete questions. So maybe one or potentially two questions, because the materials we have are chapter 3, chapter 4, chapter 5, and groups. So one of these things is going to have two questions. Um, chapter 5, we have done very little of chapter 5. Chapter 4 is Mac. Chapter 3, large part of it was already on the exam, right? So uh, one of these two things is going to have two questions. Okay. Comparatively, groups are easier, but since you haven't had a homework on that, I'm not going to say no, you'll have two questions. Okay. Once again, there will be two timings available for the exam, 2:35 and 10 o'clock. Choose one of them. I am fine